Alpha Centauri, a trio of stars 4.37 light-years from Earth. They are the Sun's nearest neighbors. There are now hints of something else in this system. A planet. If it's there, it orbits too close to its parent star to bear life as we know it. If we find other planets there, especially one resembling Earth, some say that will ignite an effort to build a vehicle powerful and speedy enough to get us there. Interstellar flight is part of a long-standing quest to expand our horizons and go where we've never been. What imperatives will define our first interstellar mission when it finally launches and finally arrives? A future journey beyond our solar system has been compared to the great human migrations of the past. One of the greatest spanned the uncertain reaches of the Pacific Ocean. It began 8,000 years ago with the arrival of people on Taiwan, off the coast of China. By around the year 1200 AD, their Polynesian descendants arrived at their furthest point, Easter Island. In 1,000 small journeys, moving from island to island, a seafaring culture emerged. What are the Tongas, the Fijis, and Easter Islands of the future? Astronomers are now searching in the near regions of our galaxy. They have identified 3,841 planetary candidates. Nearly 1,100 have been confirmed. The vast majority are Neptune or Jupiter-sized planets that orbit close to their parent star. By one recent estimate, based on data from the Kepler Space Telescope, our galaxy has 9 billion stars with planets roughly the size of Earth, with conditions that could support life. The nearest possibility is a 3-star system called Alpha Centauri at 4.37 light-years away. It's the brightest star in the southern constellation of Centaurus. Proxima Centauri, a red dwarf, is the closest of the trio, but so far no planets have been detected. Alpha Centauri A is slightly larger and more luminous than our own Sun, while B is slightly smaller. A team of European astronomers working at the European Southern Observatory in Chile recently detected a subtle wobbling in the light of B. It could be a sign of tugging from a planet's gravity. If a planet is there, it literally hugs its parent star, with an orbit that's even closer than Mercury is to our Sun. It's probably molten, with surface temperatures in excess of 1,000 degrees centigrade. Are there other planets far enough out for liquid water to flow? That prospect is the subject of intrigue in science and science fiction. Alpha Centauri is the fictional location of Polyphemus, a giant gas planet, and its moon Pandora, from the movie Avatar. The year is 2154. Earth has been ruined by environmental catastrophe. Greedy prospectors board the hybrid fusion antimatter spaceship, Venture Star. They descend on an innocent hunter-gatherer people called the Na'vi. Could such a place exist this close to home? One problem with Alpha Centauri is that the orbits of A and B bring the stars as close as Saturn is to our Sun. This means that planets further out could have been pulled away and flung out into space. For this reason, Alpha Centauri was not a high priority for planet hunters. That is, until similar examples turned up, such as Kepler-16. 16b is a planet that orbits two stars, which in turn orbit each other. Or Gliese 667, a triple star system 22 light-years from Earth. 667c is a red dwarf, 1/3 the mass of our Sun, with 6 planets in its fold. 3 of them, small enough to be called super-Earths, orbit at a distance that could allow liquid water to flow on their surface. That opens the possibility that planets may have survived in the Alpha Centauri system. For now, that question is on hold. The orbits of Alpha Centauri A and B have brought them too close for astronomers to resolve the signal of a planet. When they move apart again, astronomers will have new tools at their disposal, including the James Webb Space Telescope, now set for launch in 2018. From a position 1,000,000 miles away from Earth, it will deploy a sun shield the size of a tennis court and a mirror over 21 feet wide. Astronomers will use this telescope with its infrared light detectors to discern the chemical composition of planetary atmospheres. Here are Alpha Centauri A and B, as seen by the Cassini spacecraft just above the rings of Saturn. Assuming it's worth the trip, you'd have to travel a distance 30,000 times the orbit of Saturn to reach them. Put another way, if Earth to Saturn is a meter, then Earth to Alpha Centauri is New York to Chicago. To put the journey into perspective, consider Voyager 2, now on its way out into the galaxy. After a series of gravitational assists from Jupiter and Saturn, the spacecraft is traveling at about 62,000 kilometers per hour. If it were headed in the right direction, it would need another 73,000 years to reach Alpha Centauri. The dream of traveling to other solar systems was forged by rocketeers a century ago. A Russian schoolteacher, Konstantin Tsiolkovsky, inspired generations of space visionaries with sophisticated ideas about multi-stage launch vehicles. He imagined the construction of space stations in Earth orbit and eventually permanent space colonies. Someday, he predicted, we'll evolve into a whole new species, Homo cosmicus. Since then, rocketry's greatest advances have centered on ways of containing explosive propellants and methods of maintaining stable flight at high speeds. The problem with chemical rockets is that they are just not very efficient.
3 engines up and ready. 3, 2, 1.
To reach the speed needed to escape Earth's gravity, 25,000 kilometers per hour,
Blazing a trail to scientific discoveries aboard space
the space shuttle carried 15 times its weight in fuel. A NASA study showed that to send a shuttle-sized craft to Alpha Centauri in 900 years would take an unbelievable amount of fuel, 10 to the 137th kilograms worth. That's more than the entire visible universe. There are several promising advanced propulsion concepts on the drawing board, including fuel-efficient plasma engines, which accelerate a spacecraft gradually to high speeds. It won't get us to Alpha Centauri in anything close to a human lifespan. To go that far and that fast, a pre-Apollo project called Orion called for a series of controlled nuclear explosions to propel a spacecraft to high speeds. The project died amid concerns about the impact of nuclear explosions on the environment. Back in the 1970s, a group of scientists unveiled designs for Daedalus. This giant fusion-powered craft would have had to carry 50,000 pounds of fuel. The plan was to accelerate to 12% the speed of light and reach a nearby star in 50 years. Other plans have included ramjets with vast magnetic fields that scoop up a fuel supply of hydrogen ions, or solar sails powered by the solar wind and by lasers stationed along the way. Then there's the rocket of choice in science fiction, powered by the most potent fuel in nature, antimatter. In James Cameron's Avatar, a fusion antimatter hybrid engine powers a 1,500-meter-long spaceship. It makes the journey to Alpha Centauri in just 6 years. Antimatter consists of electrons and protons, but with their electrical charges reversed. Whenever it comes into contact with normal matter, the two annihilate each other in a ferocious blast of energy. Only trace amounts can be found in the universe today. For example, in the high-energy environments of black holes. It's so powerful that a mere 10,000th of a gram is about all it would take to send a spacecraft to Jupiter. Current designs for an antimatter drive use magnetic fields to isolate and channel the fuel. The idea is to merge a stream of protons with a stream of its antimatter opposite, antiprotons. A magnetic field pinches or compresses the combined streams into a narrow beam. Annihilation then produces an ultra-high energy laser that shoots out the back of the craft. That causes a recoil effect that pushes on the magnetic field produced by the beam and propels the craft forward. Antimatter can be produced on Earth in giant physics labs like the Large Hadron Collider. Here, scientists accelerate atoms to nearly the speed of light and blast them together to release their fundamental constituents. The yield is so small that the cost of producing just a gram's worth of antimatter would be upwards of $100 trillion. And the stuff is so volatile that storing more than a few atoms at a time remains a significant challenge. If specialized facilities were built, the cost could drop, by one estimate, to as low as $10 billion per gram. One idea would be to station an antimatter factory in space, powered by the 1 billion watts per kilometer delivered by the sun. Another is to harvest antimatter already produced in space. The idea is that cosmic rays, interacting with interstellar particles, send about a kilogram of antimatter flying into the solar system every second. Some of it has been shown to circulate in radiation belts that surround the Earth. Theoretically, it could be captured by a large magnetic scoop that sits in a high orbit above the planet. Short of traveling to another solar system, there may be good reasons to develop antimatter propulsion. An interim mission would speed beyond the orbit of Pluto, sending back close-up images of objects in the Kuiper Belt. A longer-distance probe could reveal new details about the Oort cloud, a vast realm of comets that envelops the solar system. Once out there, it could sample interstellar particles or deploy an interstellar telescope. To make it all the way to Alpha Centauri within 50 years, an antimatter probe would have to accelerate to around 10% the speed of light, over 100 million kilometers per hour. High velocity has its perils. At such speeds, even dust has enough mass to destroy the craft. A magnetic shield would be needed to clear the way. If it could be done, there may be other destinations to consider. At least 22 stars within 12 light-years of Earth. Any way you look at it, the first interstellar voyage will be a quantum leap for humanity. The urge to reach out to distant horizons, to climb the highest peak, is a vital part of human nature. But explorers of old set off not just because it was there. At times it was greed, hunger, fear and despair that propelled them from their homelands and allowed them to endure their long journeys. What imperatives will send future generations into space? To the physicist Stephen Hawking, it's a question of survival. I don't think the human race, he said, will survive the next 1,000 years unless we spread into space. There are too many accidents that can befall life on a single planet. We can't foresee the impact of wars, social upheaval, or the course of human civilization in coming centuries. But an early context for the mission may be emerging now. On one hand, the technological advances that might make such a mission possible could revolutionize many other aspects of life on this planet. The ever-increasing number of transistors that can be placed inexpensively on a computer microchip has become a metaphor for the advance of technology. Some observers forecast a steep rise, even an acceleration, in the pace of invention and basic research, and for whole new solutions to the problems of energy, food production, health, and more. In addition, Despite the daily drumbeat of violence and war, we are actually living in one of the most peaceful eras in human history. Over the centuries, the number of people killed in battle has steadily dropped as civilizations evolved. With 2 world wars, the 20th century was pretty bad, but the 19th was even worse. In terms of deaths per 100,000, from war, genocide, murder, and other factors, the world is relatively calm. On the other hand, major periods of scarcity and suffering may loom. The last century saw the world's population grow from less than 2 billion to nearly 7 billion today. It may reach 9 to 10 billion by the year 2040. According to a recent UN report, the world will have to produce 70% more food by the year 2050, and at least that much more energy to sustain its population. Simple, clean water in some regions is already extremely scarce. Now throw in environmental impacts like rising sea levels, or the spread of deserts linked to a gradually warming climate. No matter how you look at it, our world is changing in ways that will impact the way we live and relate to each other. Will technological advancements allow us to halt the degradation of our natural environments and increase the carrying capacity of our planet? Will we find ways to mitigate the effects of war, natural catastrophes, or political upheavals? The technology needed to launch a first interstellar mission is certainly decades away. The actual journey could take centuries. The mission will likely be designed to relay basic information on a world whose light we have studied intensively from afar. Back home, it will no doubt spur reflection on who and what we have become as a people, as a planet. As our cosmic emissary makes its way across the void, we on Earth will continue to struggle in our pursuits of happiness, prosperity, and mere survival. When it arrives, we'll scan the data for evidence of a world like our own, one that may harbor life. Will we come to explore and expand our knowledge, or to begin a long journey out into the uncertain reaches of the galaxy?